All right. So in the last class, we defined the basic working of an AI device, an intelligent system, which is based on this graphics, that an AI system is made of an agent, which is sensor and an actuator. And in between the sensor and actuator, there is this agent which converts which takes the inputs from the environment through the percept sequences and decides what action to take. And then we also talked about this rational agent is an idealization of the agent. That is, we want to have the best mapping because we define a performance measure and we say that this performance measure should be maximized and the best action should be selected by an agent. So an agent which can select the best outcome or the best action and send this best action or instruction to the actuator is a rational agent. But in reality, we may not be able to get the best mapping. A rational agent should give the best mapping between percept sequence on the one hand and the agent action on the other hand. So prior computation of these mappings is not possible. So actual agent may not always give the best answer. Sometimes we are happy with the suboptimal or less than the best answer. So many actual agents may behave like this. So we also discussed in the last class how to quantify the rationality of an agent. It is defined in terms of what we call a performance measure. We said that an intelligent system will have a certain goal, and if that goal is being achieved with the best performance or best measure, which may be defined in terms of accuracy of the goal or which may be defined in terms of the distance to the goal. So these performance measures define the criteria of success. And we also discussed last time that you cannot have multiple performance measures in the end because the optimization can only be done for a single performance measure. This single performance measure may itself may be a combination of multiple goals. So for instance, a self-driving car should be safe, should also take you to the destination in the fastest possible manner. So although look like they are different goals and objectives, but they should always be combined in a single score, which is maximized for determining what mapping from the environment to the actuators should be provided by this agent. So agents may also have prior knowledge of the environment over a time when the agent operates in reality. So it also gets exposed to new environmental conditions. So it should be aware of the environment in the past and current environment. So that way, for the current environment, number of sensors are attached to it, which provided the information about the environment. So the actions and then the percept sequences to the date, these are the basically constructs of a machine. Now, another term that we must be familiar with, the autonomous versus designed agents. So we are saying that a rational agent is one which takes the percept sequence from the environment and performs certain actions, maybe through computing program or anything, and that determines some outcome to be sent to the actuators. Now, whether these decisions are being taken autonomously or they are inbuilt into the system from the beginning. If they are inbuilt from the beginning in the system, they are called designed agents. And if they are being adapted over time, they are called autonomous. So as the bullet points on this slide say, a rational agent-based machine will have some decision-making capacity at the start, incorporated at the time of design. So this is what we call the designed agent. So when you initialize, so it is like initialization or initial decision-making capacity of the machine. And the rational agent in that machine already has some capacity to take the decision, but over time, this exact mapping between the environment and the actuation will continue to change. That is called the adaptation. So as the second point says in the bullet points, the further adaptation will be introduced by way of learning. And that is where the machine learning or other learning-based heuristics will appear. And then the third is the point is that autonomous systems rely on adaptation, whereas prior design comes at the cost or prior to agent being able to act autonomously. That point already made clear that there is an autonomous a working of a machine and there is a designed working of an agent. Do you all understand this? This seems to be quite obvious, but can you just confirm that you understand the difference between a designed agent and an autonomous agent? Can any one of you say something more and probably give some examples? Any of you? Are you people there?
Yes, sir.
Yes, Aditya. Can you tell me, you understand the difference between these two? And can you give me some examples if designed and autonomous?
Yeah. So what I could get is that designed agents are the one in which we have from the start a certain set of ways that they would act in the environment.
Yeah.
It is designed into them. Why autonomous systems rely on adaptation, that is seeking information from their environment and get adapted to the conditions that prevail in that environment without so they develop features which were not initially designed into them.
Yes. So can you give me practical example? You understand it correctly. There is a definition. But can you give example from your real life situation? Think of an agent or think of anything, any intelligent system, be it artificial intelligence system or be it a machine, which has a design part of it and autonomous part of it. Or you can think of a child and find an equivalence between the designed agent equivalence in a child's actions and an adapted actions. Can you give examples from them?
If I coming to think of a child, I would say that some features of it would be I would say that it is designed such as I can think of the basic features of a human, that is that it is not a like it's there like the ability
reflexes,
to
like the natural
reflexes,
reflexes or instincts.
Yeah, whereas the ability to perform conversations or to come up with creative language, that I would say is something that is adapted by the child.
Yeah, so any agent, so in any scenario, when we go for the first time, we have certain predisposed notions how to act in that situation. And when you are attending a class, when you are appearing in an exam, when you are doing an action in your, when you are interacting with people, then you have, when you enter that environment settings for the first time, you come with a prior set of things that if you experience this, this is how you will act. If you are hungry, this is how you will ask for food. If you need this, that is how you will do it. This is the prior. When you enter into this new environment, you enter with certain design agent inside you. This is equivalent I'm giving from the machine. Instead of machine, I'm giving you a human behavior, how we do this. Same way, when a machine you are installing, initially it will act according to certain prior programs, that if this is the, for instance, vacuum cleaner or the air conditioner, it will take certain decisions. If this is the temperature, that is how it should act. So this is a kind of designed agents where the instructions have been pre-installed in it. Now, over time, the machine will learn. For example, if you are interacting with society and you have certain ways of interacting with people, you want to make friends, but you find that you are not making friends in this way. So you adapt and you develop new ways of making friends. So this is the autonomous or adaptation that you are introducing into your personality. And in response to that, you are adapting. Same way the machines will adapt. But here, how will you know that some changes are required? Yeah, Aditya.
Yeah, I had a question. So in the case of autonomous systems, shouldn't it be the case that the environment would penalize the system so as to get them to adapt?
Exactly. Excellent. This is what I was coming to. So that this adaptation cannot happen without a feedback mechanism or without some way of assessing whether the performance that you have defined, you are defining performance. Like in the example of making friends, I said, you have a score in your mind. Am I making friends? This is the question you are asking. And then you are getting the feedback, no, you are not making friends this way. So there has to be some measure of performance measure that these actions are leading to these outcomes. And that has to be scored. So there has to be a mechanism to monitor the performance over time. So that is how you get that is the point you're making, right? Or you're saying something else?
Essentially getting penalized by the environment.
Penalize means feedback mechanism.
It
may be a reward. It may be a reward. It may be a positive feedback or a negative feedback. So, but that will be based on certain goals that you set. That these are my goals. Whether this goal is being fulfilled or not, that is the feedback. So you get positive feedback and negative feedback. Based on that, you learn or you adapt. That is how the machines will also adapt. So if
is it like back propagation in neural networks?
Yeah, so like if you can think of a neural network, backpropagation also works in the same way. So you get basically backpropagation is not the only way. What it's you can think of the best equivalent will be that you have an error function, and based on that error function, you get you need to update your weights. These update of the weights need not be through backpropagation only. There may be other methods. So you have rightly thought backpropagation is a mechanism to do this, to propagate these weights backwards. And how they actually, the goal is to modify the weights. So basically to let the machine respond differently. Initially, when a neural network is initialized, you have certain inputs and you have certain outputs. This is like designed agent. Now, over time, you are getting new instances and you are getting an error function, which is telling you that the outputs that the neural network is sending in the end is right or not right. If it is a classifier, it will tell you what percent is the correct, the accuracy of the model. So it will say, no, accuracy is not good, so please change. So the mechanism of adaptation may be different. So backpropagation in this way is one form of adaptation, but there may be other ways. Somebody may learn through random associations, just randomize, keep on trying different weights and achieve one. So they will come to this, how we actually, how we let the machines adapt. But adaptation method, backpropagation is yes, one method of adaptation. But adaptation simply means that modifying the behavior of the machine or behavior of the individual so that the responses that are elicited from the same inputs in the beginning will be modified in the after the adaptation. New outputs will be generated which were not being generated in the designed agent. Why they are being new generated? Because it should maximize some performance measure. Because the designed agent was not optimized over a time, it is optimizing itself. Right? You get this point? Or you want to make any more comments on this, or you have any thoughts?
So the constant thing with autonomous systems is just the task that they are defined to do. The way that they achieve it would adapt over time.
No, that depends again on how the autonomous system is designed. Autonomous system may be designed by way of a neural network, or it may be designed through some other method. So this is the algorithmic part, how you make the machine adapt. But as long as it is adapting and as long as the performance measure is improving over time, we can say that the machine is adapting or it is autonomously acting so as to improve the performance measure. Right? You get it? Or if you want to add something that is coming to your mind, you would like to add to this? All right, then. So you pretty much understand that design is kind of the initial network. Now, again, when we are saying design, it is slightly different from random initialization of a network because this design may have been done by somebody who designed the machine. They will put minimum functionality on when to switch on, when to switch off. For example, if you are running an air conditioner and you want to design the decision of switching on and off, maybe in the beginning, the design is that every 1 minute it should switch off, or after 2 hours it should switch off. At such and such time it should switch off, and such and such time it should turn on. So these may be the designed things that the machine starts with, which may have been deliberately placed it, keeping a general scenario in mind. But when it is actually installed in real situation, then that particular environment, a special environment in which this machine has been placed, has to be considered. And then over time, adaptation will help. So why adaptation is being done in real time is because every environment is specific, and intelligent machine should be able to understand the environment in which it is operating. Otherwise, you can have simply a new type of mathematical formula that if I'm taking inputs from 10 sensors, these 10 sensors inputs should be combined in this particular mathematical expression. And then that is how the decision of turning on or turning off the air conditioner should be taken. That will be designed. But autonomous means in every room, the conditions are different. Only certain certain features which are contributing to the decision may be important in some cases. In some cases, more be important, and there may be different weights to this. So this part will go to machine learning, and what method, what algorithm you are introducing here will be selected. But as long as the machine is adapting and improving the performance measure over time, you can say that this machine is autonomously acting and adapting to the environment. All right, so we go to the other examples here. This, now you can think of this intelligent system or an intelligent machine to be made up of 5 parts. 3 parts we introduced earlier, which were an agent, and actuator and the sensors from there. So this is what we discussed last time. We have a sensor, we have an actuator, and we have an agent. Now, if we specifically see how this task environment take the environment also into account and the performance measure also into account, so we can define every intelligent machine to be made up of 5 parts. One is the agent type, who is the agent and what is the agent in this case, and what is the performance measure. As I said, we have to define this quantitatively as a single scoring system, and the environment, what is the inputs being taken here, which may be roads, other traffic, police, pedestrians, etc. And then the sensors, which are these devices in this example of taxi driver, and actuators. So this every task environment of an intelligent machine can be described in terms of these 5 components. And this is the example that has been placed here, that an agent taxi driver takes a decision about, let us say, turning right or left, or choosing a particular path out of a number of options that he has available to him. So you have to now define your performance measure. You want the driver to go very fast, or you want to driver to be very safe, and what are the legal conditions, whether passengers sitting there are comfortable or not, whether the profit money, because if the driver goes faster and if the driver takes longer route, maybe the company is making more money, and then impact on the other road conditions, and maybe also some conditions which may have not been written here. Can you think of additional performance measures that may be applicable if you are designing a taxi driver, an agent which is replicating taxi driver? Some performance measures, some components of performance measures are written here, but can you think of additional ones? Just give me one more.
Could you,
yeah, please.
could you clarify this minimize impact on other road users? I didn't quite get that.
When a car is driving, then it will affect the other cars on the road. So you're not letting them go. You're not letting overtake you. So how your car is influencing other cars on the road, or other pedestrians on the road, anybody on the road, other than your own machine. So any action that you take on your car also influences the environment around you. You might want to give some weightage to this factor also.
Yeah, okay. And when you say safe, do you account the safety of the passenger, or also the safety of the pedestrians that move
Probably
around?
in this example, I have taken this from Russell and Norvig. So probably in this example, safety refers to the driver and the passenger in the car. But you can define, maybe you can be more specific that you are talking about safety of the driver or safety of the passengers inside the car. So if you are thinking of safety of the people outside, probably this will be counted in the minimizing impact on the other road users.
But say the weight that we give to it, it should be high.
Weight? Yeah, so that you will decide. So this is, these are these you will first have to define them in a measurable manner. So these are general goals. Now, as an engineer, you will have to say safety will be defined as, how will you define safety? Safety will be defined the probability of an accident, or the time of the probability of coming close to another car by this distance. So this is not straightforward. You cannot define safety just like that. So we'll have to find some scoring system which can tell, okay, this is the safety score. And then same way, you will define what is fast, the time taken to the destination in this case, or something else, maybe every time, average time, or so whatever is the case. So you will define fast. You will also define legal, whether for instance, if you just make your autonomous taxi driver to go fast, it may want to jump the red light. So legal considerations will then appear that you have to wait for the red light. How far you want to be compliant with the law, that also has to be incorporated into this. And then comfortable trip, maximize profits. So these points. So can you think of any other additional factor that can be incorporated into the performance measure? So this I'm making you think, because you should not just think that these are the gold standards of the performance measure. This is just a notional list of performance measures which have to be combined. So in this notion, you can add your own thoughts, and you can say, yes, this also should be included in the performance measure. So for instance, you can use the fuel consumption. You can use the wear and tear of the tires, right? So these are.
Wouldn't that all be included in maximize profits?
Well, yes or no, not necessarily, because you might have fuel efficiency on the one hand, and well, maybe you're right. Maximizing profits may include this. Then can you think of something else in that case? Maximizing profit. Yeah, let me clarify my thoughts too. Maximizing profit different from fuel consumption, because maximizing profit may also mean that you want to have maximum number of trips possible, and go to longer distances for a distance that can be covered in 1 hour, or a destination that can be reached in 10 kilometers. You want to take a 20-kilometer route for that. So profits can be maximized in this way also. So therefore, if you are looking at the fuel consumption aspect of it, or the pollution aspect of it, or the smoke coming out of it, so probably that can become additional factor to consider. These are my thoughts, but yeah, there's no one-to-one answer to this question. These are just thought-provoking discussions. So broadly, you understand what we mean by this. And the environment is the environment that we are dealing with, the roads, the other traffic, we already talked about it, the policing, traffic controllers, pedestrians on the road, customers, weather, these are the environment. And the actuators, we already saw, the steering, accelerator, brake, these are actuators. Now, you see that—
I guess we could add responding to enforcement, your enforcement officers.
You mean in the performance measure?
Yeah.
And for how, you mean, how will you do this?
Yeah, just means that suppose if there were to be a case in which the car doesn't follow some rules and some enforcement officer is behind it. So
legal is so basically, right?
Yeah.
Yeah.
No, if it doesn't, this factor is not obeyed properly. So in that case, if a enforcement officer pursues it, then how does it respond to that?
Okay, the response to the external disturbances or legal interceptions, you mean that, right?
Yeah.
If there's an interception from somewhere, how do you respond to it? So that can become, are you able to respond immediately? If somebody is waving hand, so are you responding to that waving of hand or not? That can be considered. So yes, so there can be multiple thoughts. So you see, when some company designs an autonomous car or an autonomous agent, they have to consider all this, and they have to standardize their performance measure. This takes a long time to standardize it. This algorithm that designs the performance measure is not a straightforward thing that you sit down and create one formula. They will have to consider so many factors, previous data, and the legal implications, all these implications, and then they define their performance measure. Ultimately, all this will be reduced to a single score, because decision has to be one. You cannot have multiple decisions. Okay, so this pretty much gives a good understanding of how we define the task environment of an intelligent system, or an agent, as we can call them, rational agent. So they will work on 5 components. What is the agent type, the performance measure, the environment with which the agent interacts, the actuators and sensors, which are physical devices. These are additional examples here. So if you, for example, look at the medical diagnostic system, so this is again, this agent is a software which is providing you a diagnosis. What is the disease based on the data that the machine receives? Now, performance measure is how do you define that my diagnostic system is working very well? Now, let us discuss it in a practical example. Suppose you are designing an agent which tests COVID positive cases. So what will be the measure to decide the performance of this diagnostic system? Suppose you designed a new diagnostic system which will take certain environments. It will decide whether the patient has COVID or not, does not have COVID. So how will you define the working of such a performance measure of such a machine? Give your thoughts, independent, any thoughts, not necessarily coming from this table, just think fresh and tell me, how will you say that this diagnostic system is working or not working? What will be the quantitative measure of performance?
So we will compare its percentage of correct predictions and correct diagnosis with that
So-
of the correct predictions by an actual doctor, human doctor.
So yes, this is an important point, that in order to compare this, we should have the correct answers for some of them. So that's why in your case, you are saying correct answers are from the doctor. An autonomous system will try to reproduce what the actual doctor is producing. Let us say this is our assumption. Whether this is valid or not, that is another matter, but this is, let us say, our assumption that a diagnosis which is being provided by the doctor, machine should also be able to give exactly the same diagnosis. Now, think of a situation. I mean, this is not a straightforward question. I'm just trying to motivate you towards this thought, that think of a situation when only 1% of the population are COVID positive. And now I have a device, I am creating a software system which declares that everybody is COVID negative. That means it fails to detect a single COVID positive case. What will be the, according to your definition of accuracy that you just mentioned, what will be the accuracy of such a system?
99%.
99%, right?
Yes, sir.
So is it useful?
No, it's quite useless.
It is useless. So that is actually, in machine learning, you will come across this kind of problems that we have when you have high class imbalance, that accuracy scores may be very misleading. Like in this example, accuracy score is very misleading. I'm declaring everybody negative and I'm still getting 99% accuracy. So that means my performance measure in this particular example has to be aware of the fallacy in the overall accuracy of counts. Can you think of any other score? Just quickly.
In my view, the number of false negatives should be very less.
So number of false
Negatives.
negative.
That means if a certain person has it, then the test shouldn't say that the percentage in which the test says it doesn't have it should be very less.
So you are already, in your mind, you are giving a higher weightage to correctly detecting a positive case and less weightage to correctly rejecting a negative case. So you are already giving some weightage to false positive and true positive. In your mind, you are saying true negative is not so useful. True positive is more important in this case. And therefore, my performance measure should give more weightage to the true positive cases instead of the true negative cases, right?
Yes.
So that is how you will define new performance measures. So like, the F score and the Matthews correlation coefficient, and there may be other scores that you will have to work out. But this is just to highlight the fact that a performance measure itself is not straightforward. It has to take into account if it is a class based decision making, if the agent is working on class level prediction, then it has to take into account the class imbalance. And if it is quantitative data, it has to look at the distribution of my quantitative values, so that a performance measure can reflect not just the overall accuracy, but also the usefulness for improving our agents, working of our agent. So again, in this case of medical diagnostic system, patient, hospital, staff, these are the environments. And because the diagnostic system operates in this case, a patient is there, a staff that is taking the readings, these are all environment. And actuators are display of the questions, if it is based on question answer, or if it is based on certain blood sample or anything, so test, diagnosis, treatments, these are the actuators. And sensors, maybe touch screen, voice, entry of symptoms and finding. So this is a diagnostic system example. So these are additional examples you can have a look at in this book and try to go through them and think of your own examples. Now, another thing about the agents, the rational agents, is they may be virtual or they may be physical agents. Physical agent may be an individual human being, or maybe a microprocessor, which just takes the input and converts that into the output, or it may be software which does calculations in the real time. I think it is very much what we have been discussing. So in terms of the properties of the task environment. So we have defined the task environment into 5 components: the performance measure, the agent type, the environment, the actuators, and sensors. So these 5 may have different properties. Let us look at the first one, which is very interesting: the fully versus partially observable, where relevant environment is obscured by noise or technical limitations. Let me take a more practical example. When suppose a car, again, car navigation is a very good example which we frequently use for defining intelligent systems. So let us say a car navigation system has to start at some location and it has to reach at a destination. And now it wants to take the best decision. So there may be a situation that it has to consider all the possible routes. Now, these number of routes that it can take may be thousands and sometimes infinite, sometimes finite. That is the finite versus infinite case. But not only that, the performance measure for all the possible scenarios may not be possible to compute, because the environment in which this machine is operating is not fully visible to the agent at the time of taking the decision. Do you understand this point? Is it possible that the agent, when it takes certain actions, the entire environment is not fully observable to it, and therefore it has to take action based on partial set of inputs? Can you elaborate? Can you help to elaborate this point so we can take real examples, and then we understand when we design a machine, we will have to define whether my machine is fully observable or not. And if it is fully observable, I will use one type of adaptation mechanisms. If it is partially observable, I will use another type of adaptation mechanisms. So first, what do you think is a fully observable versus partially observable? With the hints that I have given you, can you think of examples and tell me more?
So fully observable होगा कि गाड़ी चलाना है कुछ सनी डे पे, और partially observable होगा कि धुंध वाले दिनों में जहाँ कुछ मीटर दूर तक दिख पा रहा है.
ये भी एक बात हो सकती है कि अगर उसको मुझे स्ट्रेट जाना है, मुझे आगे वहाँ पे फॉग है, so I cannot see what is there, whether there's a traffic light at this distance. So in that case, how the decision of a fully observable environment, in this case, let us say fog is the one which is reducing my observability of the route. Let us focus on this part. So how the decision taken by a rational agent which is operating in a fully observable state, that is in the absence of fog, and the one which is operating in a partially observable condition, how the two decisions will differ from one another?
So data, the amount of data change होगा.
हाँ, तो उसकी बेस पे वो जो डिसीजन लेगा,
शायद 100 मीटर तक सब कुछ कर देख पा रहा है.
हाँ, तो उसकी वजह से उसको रैशनल एजेंट को क्या चेंज करना पड़ेगा? हाउ विल ही चेंज हिज एक्शंस बेस्ड ऑन दैट? बेसिकली तो रैशनल एजेंट का काम तो डिसाइड करना है ना, तो डिसाइड क्या करना है उसको? ही हैज टू डिसाइड वेदर ही हैज टू गो फास्टर और ही हैज टू गो स्लोअर. So based on the fog,
सर डिसाइड तो सेम ही चीज करेगा, लेकिन इसकी डिसाइड करने की डिसीजंस की फ्रीक्वेंसी बढ़ जाएगी. अब उससे जैसे फॉग में से 10 मीटर दूर तक दिख रहा है, से बार-बार अपना फंक्शन अपडेट करना पड़ेगा बार-बार, क्योंकि 10 मीटर बहुत तेजी से कवर हो जाएंगे. So जो
लेकिन दोनों बातें होंगी. अगर उसको बहुत दूर का दिखाई दे रहा है तो उसको पता है कि अगर मैं यहाँ से सीधा जाऊंगा तो आगे गड्ढा है, तो वो पहले से बताएगा कि उधर नहीं जाना है, although it looks like that his destination is coming closer in this route, but he will not take that route because he can see that. But if it is partially observable, he cannot take this decision. He will have to go there first and then find out, there is some problem here, then he has to go take alternative route. So in other words, if the environment is partially observable, then the decision or the actuation decisions will be different than when it is fully observable. Therefore, the optimizations will be accordingly affected. All right, broadly understand. So, but you can think of more examples. But do you get this point, right? Everybody gets it. I want more people to participate.
Yeah, basically what I can think of is, if we, as we were talking about in the case of neural networks, so if we apply this in the case of, if we apply the system and it has neural networks, we can say that in the case of a fully observable, the learning rate would be more. That means we are more sure of the data and we can sort of adapt with confidence. Whereas in case of partially observable scenarios, the learning rate would be yes, because we are not so confident.
Since you are talking of the neural network as machine learning wealth, that means you understand that system. So let us try to take an equivalence from the neural network. What will be a partially observable neural network? I mean, when will you say that this neural network is operating under partially observable conditions? And when will you say it is operating in fully observable conditions? Maybe a rough equivalence, but maybe it will help you to understand this point. So you have a data matrix, let us say D, and you have a neural network, say N. When will you say that this N is operating under partially observable conditions? And when will you say that this N is operating under fully observable conditions?
सर अगर वो मैट्रिक्स स्पार्स मैट्रिक्स है, स्पार्स पॉपुलेटेड मैट्रिक्स, तो वो एक तरह से पार्शियली ऑब्जर्वेबल हो गया क्योंकि हमारे पास लिमिटेड डाटा पॉइंट
नहीं, डेटा मैंने पूरा दिया, मैंने
वही अगर उसकी जगह वो भरा हुआ डेंस मैट्रिक्स है।
नहीं, डेटा तो अगर न्यूरल नेटवर्क को ट्रेन करेंगे तो आपको स्पार्स नहीं मिलेगा। तो स्पार्स जैसा डेटा पे तो आप ट्रेन नहीं कर पाएंगे उसको। आपको तो मैट्रिक्स तो कंप्लीट ही मिलेगी। जो मिसिंग वैल्यूज की अगर आप बात करें तो मिसिंग वैल्यूज वाला डेटा तो उसमें यूज नहीं होगा। तो जो भी डेटा है हमारे पास, अगर आपको न्यूरल नेटवर्क्स, यू मस्ट हैव रेड द टर्म्स लाइक बैच मोड ऑफ ट्रेनिंग एंड चंकिंग and giving batch mode and what is the other called, continuous mode of it. So when you give one pattern at a time and you make the neural network learn, and when you give the entire data at the same time and you make it learn. So in one case, when you are giving only part of the data for training, or you're chunking the data and your weight updates are being determined from only partial of the data, you can think of it like a partially observable system because it does not have information about the entire data. And when you are training, you're updating your weights for the entire data. You call it, you can call it like a fully observable system. And same way, if you are taking partial derivatives, if you are optimizing one weight at a time or some weights at a time and ignoring the other weights at a time, you're taking partial derivatives of only some weights to update them. This will also be partially observable case. So, or when you do the dropout in deep learning or the machine learning methods, so dropout is somehow you make it partially observable. So these are some not exact thoughts, but kind of if you want to insist to have an equivalence with a neural network, this is what it means: fully observable, partially observable. But actually, more practically, when we say fully observable or partially observable, usually your goal is from the current state, the agent wants to go to the goal state. I will come to this point further. That you have a current state of your system or your agent, and you have a target or goal state. From the current state to the goal state, what are the different options, different paths that you have to reach there? These different paths may not be visible, may not be available to the agent, or only some paths may be available. Only the immediate paths are available. Long-term paths cannot be computed in the real time. So because the long-term paths are not visible to this to the agent, you call it partially observable. So any scenario in which all the long distance environmental changes are not visible are partially observable. This may happen because the agent works with the sensors which are providing only the immediate inputs, not the long-term inputs, and that cannot hypothetically determine if I go there, what will happen next. That may not be visible at this time. But when we reach there, more information becomes available, and then you can take a decision. Like the fog case, I do not know what is there on the traffic light, on this traffic lights. So I cannot decide. The driver has to decide whether in order to go to a location X, he should take a turn right or turn left. Because of the fog, he may not know that the left side traffic light is fully, the traffic conditions are very bad there. So he may take a wrong decision, go to the right, if it is partially observable. If it is fully observable, he will look on the both sides and he will take a decision, maybe to go to the left. So this is the different scenarios where it may happen. Another important thing to consider is, we'll come to different algorithms of finding the agent paths keeping this in mind, whether my observables are, whether my agent is working in fully observable condition or partially observable condition. And we will see that if our or agent is operating in observable conditions, we should use one type of algorithm, and otherwise it should use another algorithm. So that will be modified based on that. So second point is the single versus multiple agents. Like in gaming, you may be operating, your agent may be operating alone, and the environment may be completely indifferent to what you are doing. But in the case of game, or in the case of certain competitive actions, as soon as you take one action, the environment may get changed. If the environment is getting changed, then your actions, you thought that if I act this way, I can reach there faster. But maybe there is somebody else who is trying to stop you. And so you have to think whether your agent is working alone as a single agent, or whether it is acting in an environment of multiple agents. So multiple agents make it complicated, where there you have to consider the gaming conditions, that it is like in game. You have to think that if you take this particular action, this agent, second agent, will do this. They will take this particular move. So accordingly, the competitive. So this agent does not have to be competitive always. They may be cooperative agent. You might say, if I go that side, I can take my friend with me, and then that will be helpful to me. So this is a kind of cooperative agent. You know that on that particular route, I have another friend who can help me achieve the goal. So I will prefer to take that particular. So based on my actions, if my environment is also changing, if my percept sequence subsequently will change on my current condition, my actions, then I'll have to consider the role of the other agents also. I cannot just decide my next action based on as a single agent. Then there'll be deterministic and stochastic and non-deterministic. Can these three terms, can somebody tell me what are these terms? Or do you know what is deterministic, what is stochastic, and what is non-deterministic? Some hint is written here, but I'd like to hear from you.
Deterministic would be that we at every point know, and it is very defined that from current state, where do we go to the next state. Probabilistic would mean that all transitions from one state to another state have some probability attributed to them, and we do not, so there is no definite path. And non-deterministic would mean that we do not know where do we go next.
Can you give me an
It could be
example?
in either of the ways.
Can you give me an example of a deterministic system and a non-deterministic system? I give you one example, then I'll ask you more examples to generate from your own experience. So when you have, let us say, hydrogen in one container and oxygen in another container, and you allow them to mix, what will happen?
They would react.
They will react and water will be formed.
Yes.
So this formation of water is deterministic. You know, if these are ingredients, if this is what I do, that is what will happen as a consequence. So when the consequences can be predicted from your action, you say such a system is deterministic. All right. Now, take another example. If I go and meet somebody, I smile at him. Can I tell whether that person will smile back at me or not?
No.
So his behavior, his response with a smile is not deterministic, right? I cannot tell whether the person will smile back or not. Is it stochastic? Or it is non-deterministic?
It could be stochastic in the sense that if the person, in the terms of what is the reaction of that person to you. If it's a stranger, then we can say the probability is zero that he would smile back. But if it is someone who you meet each and every day, then the probability is high.
Yeah, so high or low, but if you can compute that there is a 60% probability that this person will also respond in with a smile. So you will call it probabilistic if you can predict. If you do that action several times, you have certain probability that out of 1000 times, this will happen 600 times. Or if this probabilistic rules is being fulfilled, you call it this process to be stochastic, where the next action has a certain probability to happen, but this probability is known. It is not completely blind. Over a time, if you keep on repeating that action, how many times this action will have, consequence will happen, that should stabilize. That should be more determined. That it is, if you throw a dice, if the current value is 6, what is the next value? It is stochastic or it is deterministic? If I throw the dice, I threw the dice, I got 6. Now, from the current knowledge of 6, I want to throw the dice again, and I want to ask you, now I'm asking you, the value on the dice that will be shown up in the next time, is it deterministic or stochastic or non-deterministic?
It's stochastic.
This is stochastic because you know in every action, every step, the probability of getting every number is 1/6. So it may not be 6. It may not happen. It may not happen 1, 2, 3, 4. You cannot tell what will happen, but you know a certain probability that with what probability 1 will appear, what probability 2 will appear. So this is a stochastic example of a stochastic. And what is non-deterministic? Can you give me an example of a non-deterministic from such examples that I gave you?
Like the example that you gave of water, like as you said that if we mix hydrogen and oxygen together, we get water. But suppose we are in our environment and suppose we found a water molecule somewhere, we cannot say that it was formed by this reaction in particular, or was it a byproduct of some other reaction?
Yeah, you're thinking rightly, but let me fine tune the example. So in the case of air, if you are just monitoring a hydrogen atom, hydrogen molecule or oxygen molecule, and you want to predict whether this molecule will go to the right from here or to the left from here, what will be the next moment, what will be the velocity of this particular molecule? If these molecules are following Brownian motion, then you cannot predict where they will go. But are they probabilistic? You can tell what percent of molecules will go this side, what will go that side. In a Brownian motion, if they are random, there is some kind of probability that is being followed. In a non-deterministic case, you cannot predict at all. That is non-deterministic. So this example also, the air molecule that I gave you remained stochastic. Because even in Brownian motion, or even if it is random, you have certain overall rules of probability that all directions are equally likely. That is the probabilistic rule that this molecule should follow.
But in your example of hydrogen oxygen, you didn't tell us the temperature and pressure conditions and whether they are catalyst or not. So the reaction might not happen at all. So it is kind of non-deterministic.
So it will be non-deterministic if all the conditions in which are affecting that particular system are not known. Then it becomes non-deterministic, right? So if all the conditions like temperature, pressure, everything, if these are known, then you can say it is deterministic because you can, from these conditions, it remains either deterministic or probabilistic. So it is possible a system is non-deterministic because all the conditions which influence the next outcome are not known. This is what you're saying, right? Okay, so these are ideas. So same way an agent, when it operates in a real environment, say the taxi driver, if the taxi driver is operating this, some of the environmental inputs that it is receiving or some of the ways it is acting may be non-deterministic. He may not have enough information to determine if he turns right, what will happen. If he turns, what will happen. So this is kind of, in that scenario, the driver is operating in a non-deterministic manner. But if he knows if he turns right, how much the distance is changing from the goal state. If he knows this condition, then it is deterministic. That if I turn right, I will get 1 kilometer closer. After this much of time, I will get 1 kilometer closer to my destination. But if he completely doesn't know where he's going, and it is like you leave a car and you do not know where that car is, you do not have a navigation system, and you just say, okay, you are in the middle of the city, reach the police station. Now, if you have no map, if you have no information about where the police station is, at what distances, so how will the taxi driver find the way to the police station? He will have to try randomly. He will have to keep trying. because he's acting in a non-deterministic way, he will have to perhaps try all the possible combinations of disposition distances unless he reaches his goal state. So non-deterministic is such an example in this case, is when he has
in
no
the,
idea. Yeah.
The taxi driver case, we can say that suppose the driver wants to know, the agent wants to know whether it would rain today. That would be a stochastic thing, or and if it wants to know, suppose there would be an accident in front of it, that would be non-deterministic.
Yeah, accident is almost non-deterministic. Yeah, because you cannot predict what is the. But some of the this is a little overlapping in between non-deterministic and stochastic, because some of the actions which look non-deterministic to us may follow certain probabilistic rule. So if we can define those probabilistic rules, you will say that this agent is acting in a stochastic manner. But if it is completely unknown and you cannot completely predict, for example, death, you can think of a non-deterministic. Because you cannot predict. Again, but somebody might say that I can tell the probability of death at this age is this much. So that makes it a little stochastic. So this is where you have to specify in your system, you are calling this to be non-deterministic or calling stochastic. And accordingly, you have to take the decision on how to reach the goal state. For example, if you want to design a taxi driver, you place a human being on the steering, but you do not know whether the taxi driver will unfortunately be able to live until he reaches the destination. So theoretically speaking, it is non-deterministic. But then somebody might say that, okay, the likelihood of a person losing his life during the taxi at this condition is so low that it is almost deterministic. Such actions can be reached. So there may be some cases, it may not be obvious whether my system is completely non-deterministic or it is probabilistic, or within the certain range of permissibility, you might call it probabilistic or non-deterministic. All right. So then your agent may act also in an environment where things are happening in an episodic manner or in a sequential manner. Can you understand the meaning? The word, what episodic and sequential means? So episodic is when certain things happen, certain events take place as like episodes. They don't happen like if X happens, then next will be Y, and then next will be Z. If there is a particular sequence of events, you call them sequential. Otherwise, if X might happen and suddenly after X, Y might happen, maybe X can happen again. So if they are like this, when events can happen randomly as episodes, you call them episodic. Otherwise, you call them. Otherwise, if they can be predicted from the current sequence of events, I can predict the next event, then they will be called sequential. Again, finally, you may have a static environment in which the machine is operating, or you may have dynamic. When environment is changing, you call it dynamic environment. And when this environment is more or less fixed, every car is where it is. Like you may be playing certain games where the entire environment is static and you have to just navigate through it. That is static environment. But in some cases, you may be playing a game where the environment around you is changing. Part may be static, part may be dynamic. So that is how your environment may influence. So this is a table that you can have a look, and where multiple examples have been provided by whether they are observable, partially observable, whether the agent is single or multiple agents, deterministic or otherwise, episodic and static, and discrete or continuous. So these are the examples you can have a look in this book. So I move to the next. Finally, the structure of a rational agent, and that is where I'll stop so we can continue next time. So you have now the architecture of the rational agent, which we have been discussed, the multiple sensors, they give the percept from sequence, you have the agent program, and you have the architecture on the environmental side where the actuators operate. Okay, so these are the actual implementations. So two types of implementations I'll discuss with you. One is called the table-driven agent program. So what the agent program is doing is taking the inputs from here, from sensors, and this is the agent, which is the agent program. And this agent program is producing the outcomes, what should be carried out as a decision. So this decision mapping can be done like a table. You just draw, if like in this example, So let us say my agent has to declare the winner from the tosses. And I want to design I mean, it may be a game, it may be just software in which you toss a coin. If it is head, the machine will tell you whether you win or you lose. If it has some hidden program from based on which it is telling whether you are winning or you're losing. So this action, the decision about winning or losing is the action, and this is the percept sequence. So when it starts, there are only two possibilities, either head or tail. This is what we discussed in the beginning, the design agent. That is, it has been designed from the beginning. If there is H, it will do head will win. If T, you say tail wins. So two decisions can be taken in this case from head and tail. Now, if you throw this coin again, what are the possibilities? It may be again head, so it will be previous was head and again head, so HH. Previous was head, current may be T, so HT, or TH and TT. So these are the four possible outcomes in the second stage. And you might declare that if both are H, head wins. If one is H and one in T, you declare tie, and this tie again. So you're not making any generalization, any abstraction. You are explicitly saying, if it is H, this is the outcome. If it is T, this is the outcome. If it is HH, this is the outcome. So every sequence, every percept sequence will be written on the left, and every action corresponding to that will be written on the top right. So you can create a table like this, and then all your agent has to do, or your machine, intelligent machine has to do, that it will take the percept sequence, it will match it with the table, and then pick up the lookup table. From the lookup table, it will tell what is the answer. You understand this table based agent? So in a table based agent,
how is this intelligent then?
Second,
how is this an intelligent?
Yeah, this may not be intelligent that way, but it is just an agent may work in this way. Yes, so because it is not autonomous, therefore you are asking, your question is valid, that this may not look like an intelligent machine. And because it is kind of creating an entire table of the possible percept sequences and converting them to an action. But theoretically speaking, if you have a machine to operate in a limited set of environmental conditions with a limited set of percept sequences, there's no need to make this machine intelligent. You may simply have a mapping. You can create a table, and you can incorporate this table into the microprocessor of your air conditioner switch. And then every time it will microprocessor will match this and it will give you the answer, right? So this may or may not be intelligent, but this is a kind of a raw or basic agent, which is functioning of such an agent is simply creating a table. So why this is not feasible is because, yeah, as you rightly pointed out, this table driven agent is doomed to fail. Why is it doomed to fail? The answers are here. Because it is impossible to store a table for most big tasks. For example, self-driving car, suppose it has 7 camera percepts and it is collecting data at 70 megabytes per data size. So creating such a table is almost impossible. So this table cannot be created. There are two aspects of it. One, you have to create this table in an exhaustive way. Second, even if you have been able to create a table, a huge table, the time to scan through that table and take a decision quickly will be hugely large. Therefore, it is two aspects have been written here. Number two, impossible for an agent to learn this table. Second, impossible to search and find the right table entry in the real time. And the key task for AI is to write an agent program efficiently in a practical manner, not in a table-oriented manner. See, in this table also, I can write a machine learning program which will take this as the input and give this as an output without having to look at the table. So this is like a big tables. Can these big tables can machine learning models learn these big tables? That is the second aspect. We might make a program which will automatically convert this into output with not so much of heavy memory, but that is a very different situation. But in general, if an agent which is called a table-based agent is not a practical agent because it cannot solve any real problem with sufficiently large outcomes. So now, therefore, in reality, you almost never work with table-based agents. You work with intelligent agents, and these intelligent agents or the practical agent programs there are 4 types of practical agent programs. So one of them is called the simple reflex agent. Then you have model-based reflex agents, you have goal-based agents, and you have utility-based agents. We'll cover them one by one in the next classes. So for now, I stop here for today. If you have any more questions or thoughts, we can discuss them.
Is in the real world, is the difference between non-deterministic and stochastic the only difference of data? Because something that the agent perceives as non-deterministic, after it has some amount of data, it can say, no, this is stochastic.
No, if the probabilistic rules are known, if we know that our system, what is the probability of different outcomes, for that the probabilistic rules have to be known, then only we can call it stochastic. If they're not known, for the practical purpose, for the agent, the system is not deterministic. If in the case of dice, I know that every outcome has a probability of 1/6. So this is probabilistic clearly. But if my dice is such that I cannot tell what percent of the times it will be 1 and what percent of the time it is 2, so it will become a non-deterministic.
Won't the agent infer probabilistic rules from the data that it has?
Yeah, if a probabilistic rule, now this question is probabilistic rules have to be known. Another is probabilistic rules should exist. If the probabilistic rules exist, then adaptation actually means this, that the system is learning and trying to understand what are the adaptation rules, what are the probabilistic rules. So it is learning that kind of thing. Yes. Very good. So this is right way of thinking, that the adaptation, the autonomous system should be able to pick up the stochastic rules by itself, but stochastic rules may not exist in a given scenario.
So would we cover Bayesian networks?
Say again?
So would we cover Bayesian networks?
Bayesian networks. So Bayesian network is a kind of a machine learning model, but we will cover first the graph-based description of agents. So that is in the next few classes. We will discuss graph-based description of rational agents, the description of goal state, and how we can reach the goal state fastest. So there we'll discuss those first. Bayesian network, I don't know if that is part of this, but if you want to learn about Bayesian network as a machine learning technique, we can do that if time permits. We have worked on Bayesian models. Maybe we can discuss them.
So will there be a quiz today?
Say again?
It's a quiz today.
Yeah, I'll send you the quiz. Okay, I'll send you the quiz after maybe 2 hours. So you'll have 24 hours to solve this. Okay, then for today, I'll take leave from you.
And sir,
yeah.
Please send the slides also, because for the quiz.
I'll share with you on the